just going to look at properties of exponents, do a little review. So let's just this stuff, right? So you've seen all this before in Algebra 1. You did a lot of stuff with this. We haven't really used it much this year, but we're about to use it a lot. So the properties of exponents. The product rule for exponents, don't care if you know what it's called, but this is what it does. If I multiply like bases, what do we do to the exponents?
Add them.
We add the exponents. And when I say like bases, let's just review something really quick. If I have something like this. Okay, that's what we're going to call a monomial later today, right? It's just a combination of product of numbers times variables to different powers. If we look at just this whole part right here, this whole thing taken together, x cubed, is called a power. You guys have seen that before, right? Okay, what are the two parts of a power? What do I call this part up here?
Exponent.
That's the exponent, right? And what do I call that part down there?
Coefficient.
Not coefficient. Coefficient would be the 2 that's out front. That's not a part of the power. Okay, it is a variable, but it wouldn't have to be. What do we call that, though? The thing that's being raised to an exponent. Starts with a B.
Base.
Base. That's it.
Good try that.
Okay, it's the base. So that's important because when we do something like this, when we multiply two powers with like bases, where the bases are the same, then we add the exponents. Now that wouldn't work. So if I had, for example, x squared times x to the 5th, what's that equal to?
X to the 7th.
X to the 7th, exactly. But what do I do if I multiply x squared times y to the 5th? Nothing. You can't do anything. It's because they're not like bases, so you can't combine them. Okay. All right. Okay, the negative exponent rule. So what this tells us is if I have a base raised to a negative exponent, like a to the negative n, I can push that power to the bottom of the fraction and make the exponent positive. Okay? So that's an important one. We'll come back to that one again and again. Okay, so now we can combine the two rules that we just talked about and derive another rule. So a to the m divided by a to the n. How could I rewrite that quotient as a product?
A to the negative n.
Okay, it'd be the same thing as a to the m times a to the negative n. I could put that a to the n on the bottom, push it up to the top, and just make the exponent negative. Okay, so I could do that. Give me thumbs. Does that make sense? Okay. Now, if we use the product rule here, if I multiply like bases, my bases are both a, what do I do to the exponents? You add them. Good. So that gives us a to the m plus negative n power. And what's another way of saying m plus negative n? M minus n. There you go. And so we come up with the quotient rule for exponents. When I divide like bases, I subtract the exponents. Okay? Let's see here. What else? Okay, there's something, one of them got skipped. One we have to do that we haven't talked about yet. How about this one? This is the zero exponent rule. If I take anything to the 0 power, as long as the number is not 0 itself, 0 to the 0 makes no sense. But any other thing, anything that's not 0 raised to the 0 power is equal to what?
Just the number.
No.
Oh, is it 1?
It's 1. Yeah, it's crazy. It's 1. It's kind of a weird thing. Later on, I'll show you guys a pattern that'll you kind of look at and say, okay, now that makes a little more sense. I'm not going to take time today. We're going to short day today. So anything to the 0 power is equal to 1. Crazy. Okay, now the power rule for exponents. If I take a power to a power, what do we do? Well, if I take a power to a power, that's when I do what to the exponents? Multiply. That's different than when I multiply like bases. This time I'm raising a power up to another exponent. Then I multiply the exponents. So what do you think happens when we have either a product or a quotient taken to a power? What can I do with that exponent?
Distribute both.
I can distribute it. Good. Now I can only do this for multiplication and division though. Don't confuse this with like thinking it's okay to do with addition and subtraction. It doesn't work that way. It makes sense that we can do it with multiplication and division though, because if you think like about order of operations or PEMDAS tree, remember that it goes P, E, and then the M and the D are together. They're on equal footing, right? Just like A and S. So multiplication and division are sort of equal to each other, and addition and subtraction also, we take those together. Those are kind of on this at the same level. So we can do for both of these, yes, we can distribute the exponent. So we distribute it to the A, distribute it to the B when I multiply or when I divide. Now, why do we have to have this fine print here? Why can B not equal 0?
Because it's a negative. It would be.
No, but I mean, what would happen if B were 0 there?
Could be 1.
Well, I mean, okay, but no, because anything to the 0 power is 1. But look at that fraction, A divided by B. Can I divide by 0? No, that's why, right? I can't, it just has to, there's a little fine print there that says, okay, this works, but remember, you can't divide by 0. So whatever B is could not be 0 there, or it wouldn't make any sense. That's one of our main rules in algebra, right? Is you can't divide by 0. Okay. All right, so now let's practice this stuff a little bit. Let's just practice these rules. So product rule, remind me what that was. A to the M times A to the N is
A to the M plus N.
good. M plus N, good. Okay. A to the M to the N power is A to the
M
Times.
times N, exactly. So let's compare two examples then. X cubed times X squared, everybody, is X to what power?
X to the 6.
Oh,
5.
to the 5th, good. That's X to the 5th. What is the quantity X cubed squared?
6.
X to the 6th. Okay, that's a really common mistake as people mix those up. All right, now the quotient rule. The quotient rule we just learned. If I divide like bases, what do I do to the exponents?
You
Subtract them, yeah. So A to the M divided by A to the N is A to the M minus N. So for example, X to the 8th divided by X cubed is X to the 5th. Yeah. Okay, what about this one? X to the 4th divided by X to the 7th. Let's take a closer look at that one. So what's that going to give me? -3, because I subtract, right? So I get X to the -3. But typically, and your assignment's going to be this way, they're going to want you to write your answer with positive exponents. So I'd have to do one more step here. What else would I do?
Over X to the 3rd.
There you go. Right? Because a negative exponent on top becomes positive on the bottom. Okay, so could we do that in one step? You can. This is not a huge deal, but I think it's very helpful when you start to do algebra with these expressions that involve lots of exponents. There's an easier way to think about the quotient rule. It doesn't show up in textbooks, but it's a good way to think about this. Instead of just automatically subtracting the exponents, think of it this way. When I divide like bases, I'm going to keep the base where it has the most power and subtract the other exponent. So I could go directly, in this case, I know 7's bigger than 4, so I'll keep the base on the bottom, and on the bottom I'll do X to the 7 minus 4, which in one step gets me to my answer, right? So that just means we can think of this either way. We can either subtract M or N from M on the top, or N, said that backwards tonight, N from M on the top or M from N on the bottom. You get the idea. Depending which one works for me, which one's going to give me a positive exponent, okay? I can do the same kind of thing with the negative exponent rule. You guys would all tell me A to the negative M is equal to what?
1 over A to the negative.
1 over A to the M, good. Okay, but I could also flip that around. If I start with a negative exponent on the bottom, like 1 over A to the negative M, what do you suppose that gives me?
Positive.
A to the M.
Yeah, a to the m on the top. So there's another way to think about the negative exponent rule also that's a little more useful, a little more general, and it applies in more situations. Just think of it this way. We always divide a fraction into two parts, right? There's the numerator on top, denominator on the bottom. That's what a fraction means. So the rule can become this. Anytime you have a negative exponent, you always push it to the other part of the fraction where it's going to become positive. So if it starts off negative on the top, it's positive on the bottom. If it starts off negative on the bottom, it becomes positive on the top. Okay. So x to the negative 4, you guys would all tell me, is
1 over x to the
1 over x to the 4th. Good. 1 over x to the negative 4 is
x to the 4th.
x to the 4th. Good. Okay, and then we had our 0 exponent rule. Anything other than 0 to the 0 power is 1. Okay, which makes short work of stuff like this. This looks pretty complicated, right? I've got the quantity 2x cubed y times y to the 9th, but that whole quantity taken to the 0 power makes it all equal to 1. Yeah. Okay, and then our product of or power of a product rule. The quantity a times b to the m is
AM plus, is it plus?
no.
AM
Times. Yeah, times. We just distribute the exponent to both factors in that product. So it's a to the m times b to the m. And then I can do the same thing for division, right? The quantity a divided by b to the m is
AM over B to the M.
yeah, a to the m over b to the m. Good. And so, for example, if I take the quantity, notice I say the quantity to indicate that it's in parentheses. The quantity 2x cubed is what?
2x cubed.
2 cubed.
Okay, not
Two
quite. I got to
cubed.
cube.
Cubed, x cubed.
Yeah, I got to cube both. I've got to cube the 2 and the x. And what is 2 cubed?
6. Wait, that's 8.
8. Yep, 8x cubed. Okay. How about this one? The quantity 2 over x.
2
To the fourth.
and x to the 4th.
Yeah, 2 to the 4th over x to the 4th, which is
16 over x to the 4th.
16 over x to the 4th. Good. Okay. And then a reminder for your notes. Don't generalize, right? Just because we can distribute the exponent when we're multiplying or dividing, don't generalize and just assume that you can distribute it when you're adding or subtracting, because it doesn't work. Think about that for a second. What does the quantity a plus b to the m really mean? When I have an exponent, like if I have something like x to the 4th, what does that really mean?
X times x.
Okay, x times x times x times x. So x multiplied by itself 4 times, right? So the quantity a plus b to the m, look what that's going to mean. That's going to be a plus b times a plus b times a plus b times a plus b until I have m, whatever m is, whatever number that is, till I have m of those things being multiplied together. That's going to be incredibly difficult, right? That's going to be much more complicated than just distributing an exponent. I'm going to have to do a lot of work to get that answer. I'm going to have to FOIL stuff out, collect, simplify, then distribute the next factor to that one and combine it all, and right? It can take a while. I'm going to get a complicated big answer. It's not that simple. Okay, last thing I'll just introduce is this idea of a monomial. You're not going to see this on the next couple of assignments, but eventually we'll get back to this, and I want to just introduce the concept today. So a mono means one. Monomial just means a single term, one term. So nothing is being added or subtracted. It's just to it, just by itself. A monomial is a number, a variable, or a product of numbers and variables. That's it. So here's an example of a monomial, right? 5x to the 6th. Let's kind of dissect this thing and see what the rules are for the numbers that show up in a monomial. Well, one number shows up as the coefficient. The coefficient just means a number that's being multiplied by variables, right? You guys have seen that many times. The other number shows up in the exponent. What are the rules for those numbers? Well, the coefficient just needs to be a real number. It could be any real number. It could be irrational, could be a fraction, could be a decimal, whatever. It's just a real number. The exponent needs to be a whole number. So it can't be negative, it can't be a fraction, it can't be a decimal. It's just got to be a simple whole number, 0, 1, 2, 3, 4, 5, etc. One of those numbers, okay? Here are some examples of monomials. A number like pi by itself is fine. It doesn't even have to have a variable. It could just be a number. A number by itself is considered to be a monomial. It could be a coefficient times a power of a variable. It could be a variable by itself too. It could involve multiple variables. I could be multiplying by multiple variables. Or it could be something like the square root of 2 times x to the 13th, because that square root of 2, even though it looks a little strange, it's just it's a real number. And the coefficient just has to be a real number. Okay, so let's, and one last thing, I guess, before we just flip the page. Again, this is not really an issue for the first, couple sections we're going to talk about, but when we get into polynomials, which is where we're going to be going with all this stuff, then this becomes something important to talk about. When we're adding or subtracting monomials like that example right there, where I've got two blue terms and a red term being added together, how come the blue monomials can be combined and the red one can't?
Because the x and the y is separated.
But why could I combine I could combine the blue terms to make a single term. I can add those up, but the red one I can't. How come the red monomial can't be added to the blue ones? Because the variables are different, right? You look at the exponents and the variables. The powers of the variables are different, so they can't be combined. Okay, we'll get back to that later. So for today, then, I just want to look at some simple examples and just practice this a little bit. Okay, so what about this first one? Simplify using positive exponents for any variables. Assume all bases are not equal to 0. Okay, good. So what's the only thing we could do here?
Distribute. Or do that.
Well, you gotta get rid of the negative.
I got to get rid of the negative, right? So really the only thing there is to do here is I've got to take this, because what's being raised to the negative 3? Is the 7 being raised? No, it's not. Only the x, right? So I've got to take the x to the negative 3 and just use my negative exponent rule. And what's that tell me? What's that going to become?
1 over x to the 3rd.
Yeah. And so what I want to do typically is I want to be able to write each term as just one fraction. So the 7 stays on top. What goes to the bottom? Yeah. The x to the positive 3. So that's my answer. Okay, make sense? No big deal. All right, try something like that one. How about? Okay, we got to take these one at a time. Each of these terms are separate. Let's look at the first one. What's the first one going to give me? 1. Yeah, it's 1, isn't it? Right? Because I've got something to the 0 power. But the whole thing, the whole 10x is being raised to the 0 power. And what's our rule? Anything to the 0 is 1. Okay. How about the next one? Let's see. We get plus, and then I've got this guy. What's being raised to the 0 there? Just the x. So x to the 0 becomes 1, but I've still got this 10 out front, right?
So it's just 10.
So it's just 10, exactly. It's 10 times 1. And so then my answer becomes, the total answer just becomes 11. Okay? Okay, a lot going on here, right? So now we might need a little PEMDAS. We only have to look at the simplifying part of PEMDAS, though. We're not isolating anything, right? We're just simplifying expressions. Okay, so what do we need to do first? Well, I guess there are some parentheses here, aren't there? So then we want to look inside each of those parentheses and see if there's anything inside that we could simplify. Well, is there anything here we could simplify inside? Nothing, right? 2 over 3 is already a reduced fraction. R to the 2nd times S to the 7th. Those are not like bases, so I cannot combine them. So, and same thing here, right? Nothing I can do inside the parentheses. So we can kind of check that first layer off. Nothing to do with parentheses. How about exponents? Yeah, look, I've got an exponent there. So what can I do with that 2? I can distribute it. Now I can distribute it, in this case, why? Why am I able to distribute it? Okay, but what's going on inside that allows me to distribute it? Multiplication and division, and those are okay, right? What if there had been addition or subtraction? No go, right? But because there's no addition or subtraction, I can distribute. So there's step number one is I'm gonna distribute that two to all the things inside all the factors inside the parentheses. So that's gonna give me I wanna try to write this as one big fraction too. So, okay, 2 squared is gonna give me a 4 on the top. What about the 3? Where? On the bottom, okay. What about when I distribute to the r squared, what am I gonna get?
R4.
On top or bottom?
Top.
Top, right? Because these are technically over 1, aren't they? Right, so that stays on the top. And what if I distribute to the s to the 7th?
That's 49.
14.
S to the
49.
14, right? Remember, when I take a power to a power, I multiply the exponents. So there's what I get from the first one, agree? Okay. Now we're gonna multiply that by the second one. I'm gonna write that as one big fraction. Anything go on the bottom? 6. What goes on the top?
Minus
Okay, 1 r cubed s. Do I need the 1 anymore?
No.
I don't need the 1 anymore because now I've got some stuff up there. I only need the 1 in the top of a fraction if it's the only thing, right? Okay, but I have other stuff up here. R cubed s. Okay, good. Now, multiplying fractions is easy. We just multiply straight across, right? When you multiply two fractions, it's essentially just like extending the fraction bar. It's really all it does. We want to take advantage here when we're multiplying this out. We want to take advantage of properties of multiplication that we haven't talked about since the very beginning of the year. Remember, at the very beginning, we said that multiplication is associative and commutative, and that was useful to us. We haven't used it that much till now, but now we're going to start. Because that allows us to do what when we multiply a whole bunch of things? If I'm multiplying a whole bunch of things together, how do those properties help me? The associative property and the commutative property. Because look, I'm multiplying a bunch of different things together, but what could I do to make that process more convenient?
Adding them together.
Well, I have to multiply.
the denominator.
Okay, but yeah, I could choose to multiply the things that are compatible together first, right? I can change the order. So for example, I could do something like this maybe. I could take the fractions and I could multiply just the numbers. 4/9 times 1/6. What's that gonna give me?
4/54.
Okay, I'm gonna get 4/54, okay? Now, what other things might I wanna multiply together? The r's, okay, let's take the r's. So we've got an r to the 4th times an r cubed is gonna give me
R to the 7th.
r to the 7th, and then finally,
S to the 14th.
s to the 14th times s is what?
That's 15.
S to the 15th, because there's an invisible 1 there, right? Okay, am I done? Could I simplify anything else? How about the fraction?
Yeah, you can reduce it.
I could divide both the top number and bottom by
2.
2. There you go, by 2.
Yes, babe. I just guessed.
Okay, good. And we get our final answer. Call it a day.
We're doing it in full today, and we're actually different because I look at it, like.
Yeah, we're learning something new.